Hey, good evening, everyone. How's everybody doing tonight? Woohoo! Excellent. Well, as always, thank you all very, very much for coming out to join us tonight. Packed the house tonight. This is amazing. Good job, you guys. So let's jump right in, shall we? 4 years from now, NASA and JPL will once again rove the red planet with the NASA Mars 2020 mission. This time, mission objectives include exploration of extremely ancient habitats to enable the collection of samples that could one day be returned to Earth. Analysis of these carefully selected samples in laboratories on Earth would transform planetary science and the search for extraterrestrial life. Tonight's speaker will discuss the evolving scientific strategy for Mars 2020, including the impending selection of a landing site. Tonight's guest serves as the Deputy Project Scientist for the Mars 2020 Lab and is the Director of the JPL Astrobiogeochemistry Laboratory, or abcLab. Research in the abcLab is broadly concerned with tracing the flow of biologically important elements through Earth systems. In recent years, his research is focused on developing analytical techniques to search for signs of life and environment in some of the oldest rocks on Earth, and then looking to understand how we can apply similar techniques to the search for evidence of life on other planets, in rocks returned to Earth from the surface of Mars, for example. Ladies and gentlemen, please help me welcome tonight's guest, Dr. Ken Williford.
Thanks. Thanks very much, and good evening, everybody. Thanks also from me for coming tonight, for coming out. It's great to see a full room of people. Thanks also to the organizers of the Von Karman series for inviting me to give this lecture tonight. It's such a pleasure to be able to stand in front of you all tonight and share what we're doing to get the next NASA rover onto the surface of Mars. So as Mark said, my name's Ken Williford. I'm the Deputy Project Scientist for Mars 2020, and I see some JPL folks here. You still have your badges on, but I know there are some people in the room, hopefully a lot of people in the room, who don't work at JPL and aren't as familiar with this kind of thing. And what it means to be the Deputy Project Scientist, of course, is to work with the project scientist. You can't have a deputy without that guy. There's two of us, Deputy Project Scientists and a project scientist, and the three of us together work to coordinate the efforts of a very large science team, hundreds of people we have already on the team, that came to us through a competitive selection of investigations that we usually talk about as instruments on the payload. So we have a number of instruments that I'll tell you about later that were selected from over 50, I think, proposals. Rides to the surface of Mars are very few and far between, so lots of people like to propose to put their scientific instrument on the rover. Several of those were selected, and each of those instruments or investigations have a team associated with them. So a principal investigator and a number of co-investigators who write the proposal together, and if selected, they become part of the science team. So that's our science team currently, all those people who wrote those proposals and had their instruments selected for inclusion on the rover. So that large science team needs some help keeping itself coordinated and managed and on task, and that's our job. We try to help the science team be as efficient and functional as possible, and we try to provide a synthetic scientific view or a vision, a guiding vision for the mission, and some of that I'll share with you tonight. So my other job here at JPL, the job I came here to do, was to set up an organic geochemistry lab that we now call the abcLab, and I did that several years ago, and it's now a functioning lab. And the kind of work we do is we work to understand some of the oldest records of life on Earth, the earliest records of life on Earth, if we can find them, and then how living systems and non-living systems have co-evolved on the planet Earth over its long history. And as we do that, we develop and apply methods to study those questions that would be relevant. They're the same types of methods that we hope to apply someday on samples that we bring back from Mars. And so that leads me to one of the things, maybe the biggest thing that's distinct about this mission compared to previous missions, and that is that we have an objective to collect a set of samples that if we're successful collecting a high-value set of samples, and NASA decides to do so in the future, or the international community decides to do so in the future, could one day be returned to Earth for future study. And as Mark said, that could be really transformative to planetary science and the study of life in the universe, to astrobiology. That's the kind of science that I like to focus on. So we call that potential effort, we call that Mars sample return, and it's a concept that's existed for quite a while. In fact, it goes back at least to Pathfinder, to Sojourner, the first rover I'll show you a picture of in a moment. As soon as NASA was successful roving the surface of Mars, became apparent that we could start to think about Mars sample return, but that's been a long time ago now, and we're just now taking that big critical first step of Mars sample return, which is the careful scientific selection of the samples that could one day be returned. So that brings me to, that was the business-like title that I usually show when I do this talk. This is the cheeky subtitle here for the Tolkien fans in the audience, There and Back Again. So that's what I'm talking about there. So hopefully we get to come back again. So I'd like to take a couple moments now just for you to all kind of gaze lovingly at this photograph of Mars. It's really a mosaic put together quite a while ago now. It's a very beautiful image of Mars put together by the Viking mission. And so take a moment. I'm going to stop talking, but I'd like you to just, when I am quiet, all the thoughts about Mars that rush into your head, all the things that you know about Mars or think you know about Mars, the images you've seen, the beautiful pictures from the rovers and the orbiters on Mars, this included, think about how much we already know about our planetary neighbor Mars. Right, it's amazing. We know an incredible amount about Mars. But now that we've done that, I'd like you to do the opposite and wipe all of that clean. Let's roll back the clock 1,000 years and take a look at what Mars would have looked like for the vast majority of human history. Yeah. So it's a tiny spot, if you're really lucky, a tiny, tiny disk of light in the night sky, slightly reddish. It had a movement that was strange relative to the stars, the other pinpricks of light in the night. But think about for how many thousands and thousands and thousands of years people looked up at Mars and all the thoughts they had about it, compared to what we know now. And so moving from here, I'd like to just take you back and just take a quick look at how far we've come. So fast forward now several centuries to the earliest telescopes, and it got so much better. I mean, look at that. That's fantastic, isn't it? You start to see a little bit of detail emerging from planet Mars, but not too much. Certainly nothing compared to what we know now. Fast forward now to 1886, and we have this map of Mars put together by the Italian astronomer Giovanni Schiaparelli. And so this is the product of a very long time. I really don't know how long, but a long time. Imagine the night after night after night, all the careful, painstaking observation through those early telescopes that was done by Schiaparelli, patiently observing and sketching and checking to see if he was correct night after night, and then adding names, building a geography of another planet. Imagine how exciting that must have been in those early days. And I'd just like to take a moment to read something from Schiaparelli's book La Vita sul pianeta Marte. Rather than true channels in a form familiar to us, we must imagine depressions in the soil that are not very deep, extended in a straight direction for thousands of miles over a width of 100, 200 kilometers and maybe more. I've already pointed out that in the absence of rain on Mars, These channels are probably the main mechanism by which the water, and with it organic life, can spread on the dry surface of the planet. Interesting, isn't it? How far we've come, but how little has changed. So this is very much, I could imagine Schiaparelli standing up at a landing site selection workshop almost and making this, stating this as the objectives for the mission. This is Mars astrobiology, was happening all the way back in 1893. But then, a couple decades later, it was all figured out, right? This is the New York Times. Percival Lowell, there is life on the planet Mars. And so Professor Percival Lowell here, observing above Arizona, looking in the skies above Arizona, observing these channels, which he interpreted as not only evidence of life on Mars, but evidence of intelligent life on Mars. Life so intelligent that it could dig canals. But let's fast forward again to the first successful flyby of Mars, the first image ever sent back from deep space. This is Mariner 4 in 1965, and this is an image of the surface of Mars. And it struck the scientific community at the time that Mars did not look like a planet that was teeming with intelligent life, but instead looked like a fairly desolate, gray, cratered surface. Now, moving a little bit forward, to 1975 and Venera 9, the first image sent back from the surface of another planet, but not Mars. Anybody know what planet this is? Venus, of course, yeah. Not a JPL mission, by the way. This is the Soviet Union had this honor of sending back the first images from the surface of another planet. It's really an incredible technical achievement. Ask any of the engineers in the audience, to have a spacecraft on the surface of Venus and have it survive long enough to transmit these images back. But the same year, NASA was sending this spacecraft to Mars. This is, of course, Viking. And this is a sort of a two-part mission that was, well, in multiple ways it's a two-part mission, Viking 1 and Viking 2, each of which had orbiters and landers. And here's an image from Viking orbiter. I meant to say on the last slide, but this is fine. That's actually, we'll go back there. So 1975 happens to be the year I was born. So if you want to have a sense of how long we've been doing this, sending back pictures from the surfaces of other planets, this is it. So I'm it. Maybe you think I'm old and we've been doing it forever, or maybe you think I'm young and this is a brand new thing. But I don't know whether I think I'm young or old, but sort of in between, I hope. Anyway, Viking orbiter, so some great images sent back from orbit around Mars. We start to see some real beautiful detail emerging on the surface, and of course, clouds. Fantastic, clouds on Mars. Now we get to the Viking landers. This is the first image sent back, as far as I know, from the surface of Mars, showing the foot of the lander there and some Martian regolith and rocks in the field of view. And Viking was very much an astrobiology mission. So the key objective of Viking was to seek the signs of life on Mars. This is distinct from the objectives that 2020 has, which is also about seeking the signs of life on Mars. Viking's objective was to seek the signs of extant life on Mars, that is, life that was alive at the time or had recently died. And so the question was, is there life on Mars currently? And to do this, in part, Viking reached out and scooped some of the soil at its landing site and brought it into different instruments within lander and did a number of biology experiments. So these results were basically negative to inconclusive, depending who you talk to. Most of the scientific community agrees, I would say, that the Viking results of the life detection experiments were negative. That is, they did not show compelling evidence for life on Mars, extant life on Mars. And so a couple decades went by of sort of a dark period for Martian astrobiology. And one of the things that turned that around was this discovery, this sort of sausagey-shaped thing in this Martian meteorite, the Allen Hills meteorite. ALH 84001s, the first meteorite collected from the Allen Hills region of Antarctica in the 1984 collection season. And this is, we believe, a Martian meteorite. So some big rock impacted the planet Mars, threw material off of the planet Mars, some of which eventually made its way to Earth and made it into our laboratories. And some people in '96, Chris Piquet and others, published a paper documenting these features Dave McKay, not Chris Piquet, published a paper documenting these features and presenting what they felt was potential evidence for fossil life in this Martian meteorite. It was very exciting at the time. Bill Clinton gave a press conference about it. So it got the attention of the whole nation. And in a sense, it launched, it helped very much to launch the field that I'm now a member of, astrobiology. The NASA Astrobiology Institute started soon after this. People had been studying exobiology before that, which is basically the same thing, but we sort of renamed it astrobiology. And so it really stirred the pot of the search for life, extraterrestrial life, and particularly life on Mars. But similar to the Viking experiments, further work was done, and most scientists, I would say, do not believe that this represents good evidence of ancient life on Mars, but it certainly got us thinking. And it helped to set the tone, and it helped to set the strategy that we use for searching for life on Mars. And we employ on Mars 2020, we will employ a strategy that's very similar to that used by the workers who investigated the Allen Hills meteorite. So the year later, we had the first Mars rover, the little trusty little Sojourner, part of the Pathfinder mission. It originally had a 7-day prime mission that was extended to 30-day mission, and it ended up surviving for maybe 54 days, I think, something like that. Here it is investigating target Yogi. And interestingly, some of the same features, some of the basic mobility system there, the basic architecture of the rover continues in our designs today. Then, of course, we get to Spirit and Opportunity, a twin pair of rovers that went to 2 different places on Mars, and in 2004. Made a bunch of great discoveries, including very good geochemical evidence from the surface of Mars for the past presence of liquid water on Mars. And then followed up by a much larger, much more complex rover, MSL's, Mars Science Laboratory's Curiosity rover. Here it is next to a drill site. You see a drill hole right there if you're close to the front, and then a mini drill hole that was drilled first to sort of test and see if this rock would be safe for a full drill. But Curiosity made many, many important discoveries and continues to make important discoveries today. One of the most important things it did was it investigated very early in its mission an area called Yellowknife Bay. And in Yellowknife Bay, Curiosity and the science team discovered some mudstones, so some rocks that originally would have been mud, probably deposited on the floor on the bed of a lake, a very ancient lake, more than 3 billion years old. And that lake would have had water in it that was circumneutral in its pH. That is, it's close in its pH and its mixture of acid and base to the water that comes out of your tap. And Curiosity determined that by investigating the minerals that were found in that rock, preserved in that rock, that were produced in the presence of that liquid water. And then it made many other measurements on the samples of that mudstone and detected organic molecules in that rock. Very, very little, but they did detect organic molecules. They measured the isotopic composition of hydrogen that came out of, that originally was associated with water, we think, in the environment of formation of the clay minerals in that mudstone. The isotopic composition of that hydrogen told us that at the time of deposition of that rock, the atmosphere of Mars had not completely escaped. So Mars today has a very, very thin atmosphere compared to Earth. But in order to have a lake on the surface of Mars and to deposit rocks like that, we believe that Mars must have had a much thicker atmosphere over 3 billion years ago with much more water. Okay. So this is a busy slide, but that's sort of the point. This shows you the missions that are currently active on the surface of Mars or planned for the near future or sort of the farther future. And so one thing to note here is all of the orbiters that we have around Mars. And it's these orbiters that give us such great scientific knowledge about the surface of Mars and really are the key to us selecting scientifically valuable and safe landing sites for our rovers. So it's only because of these orbiters and their ability to take very high resolution photographs of the surface with resolution high enough to see rocks that are large enough that could tip over the rover if the rover lands on it. That's what allows us to land such a complex and capable rover such as Curiosity or Mars 2020. And then moving out here, of course, we hope to get insight on the surface. This will study the subsurface of Mars, looking for Mars quakes, etc. Other orbiters, the United Arab Emirates is planning an orbiter in the 2020 timeframe. India successfully made it into Mars orbit. That's a fantastic achievement there. China has several Mars missions planned, including a concept for Mars sample return. So we'll see there. Note that you don't see a United States sample return mission labeled there. So we've only gone as far as to say we're planning Mars 2020. Of course, based on our success and based on future priorities, I certainly hope that we do something like this and work to get our samples back. But that's uncertain right now. And then ExoMars. So the Europeans, the European Space Agency, is planning a rover to launch also in 2020 and land at a different place than Mars 2020 and explore the surface for signs of ancient life as well. Now, moving to 2021, and I hope we see some images like this in 2021. This is an artist concept. It's a pretty detailed CAD drawing of our rover sitting in a Martian environment there. So just to give you a sense of what we plan the rover to look like, it looks very similar to Curiosity. Those of you familiar with that rover will recognize this. And a lot of the features are the same. In fact, as much as possible, we have kept the features of Mars 2020 the same as Curiosity. And we're taking what we call a heritage approach. That is, we inherit as much as possible the designs, all the hard work that went into the designs of MSL that has been and continues to be so successful, so that we don't have to reinvent the wheel, so to speak, although we are reinventing the wheels, because Curiosity had some problems with its wheels. They're degrading faster than expected. They're still doing great, and we think they'll last for quite a while. But they're degrading faster than expected, so we've redesigned the wheels. The wheels on 2020 look very different than the wheels on MSL, and we think we won't have any of those issues. So we plan to launch in 2020. We are going to keep the name of the mission Mars 2020 to make sure that happens on time. We hope it looks exactly like this. This is the MSL launch. And we will ride on a very similar, almost identical launch vehicle, an Atlas V rocket. Then we move into the next phase of the mission, which we call the cruise phase. And so this is the time that it takes us to get from outside of Earth's orbit to all the way to the upper atmosphere of Mars. It takes about 7 months, and we will arrive, I believe, on February 18th, 2021. We already know that, which is incredible to me, the people who are able to sort this out and get it accurately. At which point we enter a very short but extremely exciting phase of the mission called Entry, Descent, and Landing, EDL. Okay, and so if you haven't seen a video on YouTube called 7 Minutes of Terror, please go Google that. Don't do it now. Do it when you get home. But go check that video out. It's fantastic. It was produced for MSL to tell people about the fantastic new entry, descent, and landing system that mission used. And you see the final part of it here called the sky crane maneuver. And so many people thought this was crazy before it worked perfectly. Interesting story. So I received my job offer at JPL on a Thursday, and it was the Thursday before the Sunday on which this was planned to happen for MSL, and it was come to JPL and work on Mars sample return, and so I thought about it over the weekend, and watched with great trepidation and excitement as MSL just nailed it in that landing, and so there's this descent stage here, and the rover is lowered down on a bridle there and just touches down very softly. So this is totally distinct from the previous rover missions that used a giant bouncy ball, right? That comes down on a parachute and then in a big bouncing ball that rolls to a stop and opens up like a flower, and there's a little platform and the rover comes off. That's how the MER rovers worked. But Curiosity and 2020 are much too large and much too complex to bounce all around over the surface of Mars, and so we have to use this different method. Now, we can't come all the way down on retro rockets because that would pollute the surface of the rover and pollute the immediate landing environment, and so we hover there above the surface and lower down on a bridle, and then the descent stage flies off and crashes somewhere safe away from the rover. Then we move into the long sort of meat of the mission, the surface mission, surface operations. This is what it will look like, basically. Although these images come from the MSL HazCams, the hazard cameras that are down along the front side of the rover. We will have those engineering cameras as well, but on 2020 they'll be in color. So we'll be able to put together a set of images like this in color for our mission. We're planning for building for a 20-kilometer traverse capability. And we're qualifying our systems to 1.5 Mars years rather than the 1 Mars year for which Curiosity was qualified. And the reason for that is we have an incredibly ambitious set of objectives, which I'll go into here, that go beyond, it sort of builds on what MSL did and the objectives that MSL traveled to Mars with. So we start out, just like MSL, landing in a new landing site. It's new to us, but it's very, very old terrain, almost certainly older than 3 billion years, 3.5 billion years probably. And just like any field geologist arriving in a new place, our robotic field geologist takes a look around. So we use our scientific cameras to look around us, look at the rocks and soil or regolith that we see around us, and try to understand what was the environment, the past environment in which those rocks were deposited or put into place. What were the processes that led to the formation of those rocks that we see around us? Okay, that's sort of part one of objective one. There's a critical second part. After those rocks were deposited, maybe as sediments on the bottom of a lake, maybe as volcanic rocks put in place by a volcanic eruption. After they became rocks, they then had billions of years to be altered from their original state. Okay, and this is very important. So we want to understand the processes of formation, but also of alteration. So that's the first objective. Then we move into in situ astrobiology. That is astrobiology that is done on the surface of the planet Mars. And the first step here is to take what we are learning as we go about the geology of our landing site, about that past environment, and ask the question, could this environment have supported life in the distant past? That is, was it habitable? Could it have been inhabited? So we ask that question, and our approach to that, we basically learn from MSL. So, of course, it's very important to look for evidence of liquid water. So liquid water is basically the one thing that unites all life as we know it. At some point in every living organism's life, it requires liquid water. And so we look for evidence of liquid water, but we don't just stop there. We take the next step and we ask, just like MSL did, what was the chemistry of that water? How long did it last on the surface? Was it just an ephemeral little wispy pond, or was it a deep lake that lasted for many, many thousands of years? So those sorts of questions are important. And then we want to know what types of things were dissolved in that water, and what type of rock was that water in contact with? What type of rock could that water have dissolved, and what type of elements and molecules and minerals could have been remobilized by the water interacting with the rock and providing the food and the fuel for microorganisms? Okay, we're looking for evidence of ancient life on Mars. We're not looking for ancient polar bears and so forth, big complex life. We're looking for evidence of ancient microbial life. All right? For the vast majority of Earth history, all life on Earth was microbial. It wasn't until oxygen first appeared in the atmosphere of the Earth 2.5 billion years ago that the stage started to be set for the emergence of complex life on Earth. Okay, there are many, many ways to make your living as an organism on Earth, to metabolize many different chemical reactions. In fact, almost any chemical reaction that you can imagine, there's some organism making its living off of that reaction. We make our living off of one reaction only. We go and we seek out complex organic matter, we stuff it in our face, we breathe oxygen in, we combine that organic matter, that complex organic matter with that oxygen, and we basically burn it. We burn our food, right? You all know that. And there's a lot of energy released by that, so much energy that we can build these big bodies and big brains and so forth. It turns out, so there are organisms that live on other chemical reactions. Imagine rust. You know, rust is a spontaneous reaction that occurs in your environment, where iron is combined with oxygen and generates another form of iron. So there's some energy released there. Organisms can live off of that energy, but only very, very simple, very, very small organisms, microbial organisms. So we don't believe that Mars had appreciable oxygen in its atmosphere for much of its history, like Earth has for the last 2.5 billion years. And for that reason and other reasons, we believe Mars would have only had microbial life. So that's the kind of life we're looking for. And here's an example that you see there in that image above astrobiology. We'll talk more about what that is in a moment. So we rove around assessing habitability, and then we start to look for actual evidence of ancient life. So this is really where we step beyond what MSL is spending most of their time doing. MSL has mostly been concerned with assessing geology and habitability. They certainly have the capabilities to look for signs of ancient life. The focus of the mission has been on habitability. But we have as a core objective to seek the signs of life on Mars. And really it's been since Viking that a NASA mission has done that. Again, Viking sought evidence of extant life. We're seeking evidence of ancient life. So as we do that, maybe we'll detect signs of life, maybe we won't, but we will select sampling locations at our landing site that we believe have the highest potential in that environment to preserve signs of ancient life, or, separate from astrobiology, signs of planetary evolution. So records of the ancient changing climate of Mars. That also is incredibly interesting to us. Whether or not Mars was ever inhabited, we'd like to understand how Mars became habitable and how that habitability decreased as the atmosphere left the planet, for example. So we will choose those locations, and then we will take the next step. The third objective is to sample. So to collect samples, you see a drill hole there, drilled actually in Western Australia, but the drill holes on Mars look like that. So we will carry with us about 40 sample tubes, titanium tubes, and I'll talk more about how we'll use them in a moment, but we will use those to drill into rock. So MSL has a drill as well, but the MSL drill makes powder, turns the rock into powder, and brings that powder up into, using its sampling system called Chimera, up into a system where it can dump little bits of powder into instruments that have little doors on the top of the rover. So this is the SAM instrument and the ChemMin instrument. The SAM instrument is a very complex, basically geochemistry lab in a box that has many different capabilities, including to measure the molecular composition of organic matter and other things. And then ChemMin is an X-ray diffractometer, so it measures the crystalline chemistry, the mineral chemistry of the rock samples. We're different. So instead of creating powder, we do create powder, but that's not our focus. Instead of just creating powder and analyzing that powder, what we do is we drill a core. So we have a hollow drill bit that makes a core that's about the size of a piece of chalk or your pinky finger. And we seal that core in a titanium tube. And we can do that about 40 times. And we'll deposit those samples on the surface of Mars. And then all cross our fingers and hope that NASA decides to go back and get them and bring them back so that we can look at them in labs like the one I'm running here at JPL, or many labs, many people around the Earth and in the international community would absolutely love to get their hands, their doubly gloved, incredibly clean hands on tiny, tiny pieces of Mars that we collect. Okay, so that's the sampling objective. And then the fourth objective, also very, very important, it says prepare for humans. So the actual text of the objective says contribute to, of course it's not just us preparing for humans, contribute to the preparation for future human exploration of Mars. Okay, so I'm a big supporter of the quest to get humans on the surface of Mars. It sounds like we may be redirecting our focus away from what has been the focus, that is to get humans to the surface of Mars, to potentially the idea that we'd go to the moon kind of as a stepping stone and get to Mars. I'd like us just to go straight to Mars, but we'll see. Not my job to make that decision, unfortunately. Anyway, getting humans to the surface of Mars, I think we'd all love to someday see pictures of human beings on the surface of Mars and see pictures that they take with their camera and to hear from them in their own words what it's like to stand on the surface of another planet. I mean, imagine how transformative that would be, I think, for all humans. And so we prepare for that vision in a couple important ways. Very directly. We measure the temperature, humidity, wind, and dust environment, all the things that NASA would like to know and in order to send humans safely to Mars and have them survive there on the surface of the planet. And then we have one of our instruments called MOXIE, is a technology demonstration. It is a sort of 1% scale model. The principal investigator has described it as that, a 1% scale model of a chemical plant that could one day be sent ahead of humans to sit there on the surface of the planet and just chug away and take carbon dioxide out of the Martian atmosphere, it's mostly carbon dioxide, and convert that chemically to oxygen. Okay, oxygen would be important for humans on the surface of Mars. They could breathe it, of course, but it's also a fantastic component and ingredient for fuel for their rocket that would help them get back off the surface. A very important component of a human mission, of course. So we'll do that. Now, those are the ways we're very directly helping prepare for human exploration of Mars. But in a sense, everything we do prepares for humans at Mars. The more we know about the surface of Mars, the better prepared we are to send people there and get them home safely. So I mentioned the third objective, sampling, and I just wanted to take a brief moment to share with you something that was recently presented by Thomas Zurbuchen to the Space Studies Board. And we were all excited to see an official NASA presentation on notional sample return architectures. Naturally, NASA can be very careful with the way it discusses Mars sample return. It's a very complex, incredibly difficult proposition that combines multiple missions, as you see here. So our mission 2020 would collect the samples, but then we would send another rover away from Earth to land here on a platform. This thing you see is a rocket. We call that the MAV, the Mars Ascent Vehicle. If you watch the movie The Martian, they talked a lot about the MAV. That was a MAV that got humans off the surface. But in this case, it's a much, much, much smaller and lighter MAV that would only launch our rock samples off the surface. Maybe as a platform there with solar panels, imagining a smaller rover goes out, picks up our samples, brings them back to the landing pad with the MAV. There's the MAV launching into orbit there. And then you see this little bowling ball coming out of the front of the rocket. We call that the orbiting sample, the Oz. Okay, the orbiting sample has our little sample tubes inside, and then that Oz rendezvous with an orbiter. This is another spacecraft, so count the spacecraft here, but there are several. Another spacecraft that would rendezvous with that orbiting sample, and some piece of it maybe would detach here and fly back either to land directly on Earth or in cislunar space. So go into orbit around the moon, and then we maybe would send astronauts out to retrieve those samples. So that's the basic vision for how it might happen if it does happen. Why would we want to do that? Why would we want to return samples from Mars if it's so complicated and so difficult and takes so much time? Well, here's one reason. If we're interested in sending humans to Mars, what more precious sample could we possibly have to send to the surface of Mars and return? So it certainly seems to me, and opinions vary widely on this, you'll find many, many different opinions on this, of how important robotic sample return is to the prospect of human exploration of Mars. Some people think it's completely decoupled. I think it might be very important, if for no other reason than just the psychology of a nation or of an international community, and being willing to take that big risk to send humans there and hope to get them back safely. I think we would want to first demonstrate the capability to get some rocks back safely. Here's another reason. This is the big scientific reason. And so this is an image. It's hard to make out maybe, but what's happening here is this is on my microscope in the lab, and we're looking at a 3.5 billion-year-old rock there called the Strelly Pool Formation, and all the dark stuff that you see is organic matter. So you see a bunch of different shapes. Take a look up here, these little spheres. Maybe you have to trust me, or maybe you can see for yourself, but it's 1, 2, 3, 4, maybe 5 little spheres made of organic carbon. And then these sort of lens-shaped features, complex morphology. You have a big sphere down here with some surface ornamentation that you can see when it comes into focus. The microscope is just focusing up and down over and over through these things so you can see a little bit of their three-dimensional structure. But these are complex organic shapes. This is the scale bar here is 10 micrometers. So the width of this image is about the width of your hair. So to give you a sense of the scale of these, they're quite small. But these we would call microfossils. So this is clear evidence of life 3.5 billion years ago. So it's very difficult to see these things. You can't just go and pick up a rock in the field and take a look at it and see things like this. You have to bring it home, slice it up very thin, so thin that you can shine light through it, and then polish it to a very fine polish, then put it on a microscope, shine light through it, and you can start to see these shapes. Okay, and so we can't do that yet with a rover, so we'd like to bring samples back and look for things like these or other signs of ancient life in those samples. So here's a quick video. This is me in Western Australia, a place called the Pilbara region, northwest Australia. And this area has the best, oldest record of life on the planet. Notice I say the best, oldest record of life on the planet. It's not necessarily the oldest record of life on the planet. That might be in Greenland, depending who you talk to or believe. It might be in Canada, depending who you talk to or believe. But pretty much any scientist who does this kind of work believes that these rocks, which are up to 3.5 billion years old, do contain very good evidence of life. So another way to put it is the oldest widely accepted evidence for life on Earth comes from these rocks in the Pilbara region of Western Australia. And so a few years ago, I asked before I was involved in the mission actually, asked one of the sampling system team if they had an extra drill bit that I could borrow. And I bought this drill, and I stuck the drill bit, a Mars 2020 prototype drill bit on the end of that drill, and took it to Western Australia and drilled into these very old rocks that contain signs of life. And here's what that looks like, just to give you a sense. Oop. So notice the sound. That's percussion. It's a rotary percussive drill, or a roto-hammer. The same technology, the same basic technology that we use on MSL and on 2020. It's the same technology that climbers use when they want to drill a bolt into a rock. It's just a great way of drilling into a rock if you can't bring water along with you to cool the drill bit. You need to percuss on the rock and break it into small pieces at the interface of the drill bit so that it can cut without involving water. Okay, so that's what this drill looks like, sort of a better picture. And then we deployed the drill on this thing. And this thing is called a Stromatolite. I've got one right here. So This stromatolite that you see here is 3.5 billion years old. This one is about not quite a billion years younger, still very old, 2.7 billion years old, the one you see there. The one on the screen, we affectionately refer to as a Mickey Mouse ears stromatolite shape. You can see why. You can see there's the millimeter scale bar there. So this has sub-millimeter layering, a sub-millimeter texture. So when geologists talk about shapes in rocks, they call them textures, not like a texture you feel, but just the shape within the rock, or morphologies, we often use that word. So the morphology there is suggestive of biologic activity. Why is that? It has these very fine, wrinkly layers that you can see all there down at the bottom of the image, and then culminating there in this dome shape up at the top. And the dome itself is divided into two parts. Okay, so that's what makes it super compelling. And these are some of the most beautiful stromatolites. They're in the Tumbiana Formation in Western Australia, 2.7 billion years old. Let's just get a little closer look. And I'm just going to put this one down here. This, again, is older. This is 3.5 billion years old. This is some of the oldest evidence for life on Earth. It's a piece of a stromatolite. I'm going to hand it to someone down here. And I'd like you to pass that around. Don't worry about breaking it. Don't worry about touching it. Smell it if you want. Just take a close look. You'll see the layers in there. You'll see a dome shape near the top of it. See if you can tell which way is up there. And that is a bona fide 3.5 billion year old stromatolite. But here you get a little bit closer look on this fine scale layering. The one you have in your hand is made of quartz. This one is made of carbonate mineral. We believe these stromatolites were originally made of carbonate, calcium magnesium carbonate. The same calcium carbonate is what seashells are made of, so it's a very important biologic mineral. In that case, it's dolomite. But it has been converted over geologic time. Remember, I talked about trying to understand the processes of alteration of rocks being very important. These rocks were altered to quartz. And in that process, they may lose some of their original properties, some of their original pieces of evidence. So we'd like to find rocks that are as primary as possible, that is, that are in the shape as much as possible, the original shape in which they were formed. These rocks fit that bill. They're still original carbonate. So drilled that rock. You see some powder generated here. This is that same picture you saw before. This is the top of the Mickey Mouse stromatolite. I drilled a little bit behind it. And then took the drill bit off the drill. We just had a simple brass tube inside the drill bit, pulled that out, and this is what the sample looked like when it came out. And we think our samples as well, some rocks that we drill with Mars 2020 produce a beautiful core like a little golf pencil or a piece of chalk. It holds together beautifully. Some rocks, especially when they're layered with fine layers, it's very hard to drill them with that rotary percussive drill and have them hold together, and they form small pieces. But if you're very careful when you handle them, as the workers of the future certainly would be, working with rocks from the surface of Mars, you can put them back together in as close as possible to their original orientation. So that's what we did. This is out in the field. We did this, wrapped them in foil, brought them back to the lab, and then we did something that I doubt they will do much of if samples ever come back from Mars. We poured epoxy right down in this crack. And that was to get them all to hold together. So we commonly do that with geologic samples. If they're friable or they like to break into pieces and fall apart, we'll impregnate them with epoxy. So we'll sometimes put them in a vacuum so that lots of bubbles don't form, but we fill them with epoxy that cures and hardens. Then we can slice them in half, and we can pull a little thin slice off, mount it to a glass slide, like I said, and polish it, grind it down so it's thinner than a sheet of paper. You can shine light through it. And that's what we have here. So this is that same sample that I just showed you, epoxy impregnated, cut in half, mounted to a slide, cut off, polish, 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 thinner than a sheet of paper, shining light through it, on a microscope in my lab where we can make mosaics. Remember that Viking mosaic is made up of a bunch of images of Mars all stitched together? Same thing here. This is thousands of images. So we're using the 20 times objective, the 20x objective on the microscope, taking thousands of images. And you can't tell from that, but I'm going to show you a little video here. And we're just going to zoom in. So remember that Mickey Mouse here stromatolite. Look at the stromatolite you've got in your hand if you have it. And then see if we can see any features at a smaller scale that indicate past biologic activity. Uh-oh, here we go. Okay, so we're zooming in. You start to see that dome-shaped structure there. Okay, so in stromatolites, they're fractal in some sense. They exhibit patterns across a multitude of scales. So at centimeter scale, some of them, the largest stromatolites I've seen are as big as a person. They're 6 feet tall, huge domes. These ones are smaller domes, about that big. That Mickey Mouse stromatolite you saw was about fist-sized. But then it has layers all within it, and those layers themselves are layered and have little domes. And so you see a dome here. You see some carbonate minerals in the gray material on either side of that dome shape. And then the dark, cloudy dark stuff you see is organic matter, 2.7 billion-year-old organic matter. So that gets us very excited. So let's look closer. I said, let's look closer, he said. Uh-oh, we're going to have to do the movie again. Here we go. Okay, so we're zooming in on the dome. I won't stop it this time. We'll zoom in a little closer, and we see, what's that thing? And we zoom in closer again, and this little shape, this little squiggly shape there. Okay, that gets us very, very interested. So that may be a fossil bacterium, 2.7-year-old bacterial cell, filamentous cell. So that's the kind of thing we'd like to look for in samples returned from Mars. We can't do that sort of thing on a rover currently. We're quite a ways from having the capabilities physically to prepare the sample like that and take those sort of microscopic images. We would need to get the samples back to be able to see something like that. Then we can take the next step in our labs on Earth, and here's an image, not of the same rock, but of a filamentous microfossil, 2.4 billion years old in this case. In the top left image, marked A, you can really see that it's a hollow filament, I hope. The little box shown there is enlarged on an electron microscope in the two bottom panels. The dark material you see at bottom right that's sort of in an oval, an ellipse shape, that's the organic carbon there that's exposed at the surface of the sample from that filament. So you can see it's a hollow filament. It has a cell wall that is nanometers thick. Itself is several micrometers in diameter. And then in the panel in the top right, you see we've shot a hole in the filament. And we shot that hole so that we could sputter away the organic matter and pull it into a mass spectrometer and measure the ratio of carbon-13 to carbon-12. Why is that important? We get this number here, minus 33.2. So the ocean has a carbon isotope ratio, the ratio of carbon-13 to carbon-12 of about 0. Okay, it's sort of non-living carbon, the source of carbon for living organisms. When organisms take carbon into their bodies, either as CO2 or as dissolved carbonate ions in seawater, they preferentially take up the lighter isotope of carbon, carbon-12 versus carbon-13, and they do what's called fractionation. They change the mixture of carbon in their bodies, and they produce numbers that are far away from 0, like minus 33. You'll just have to trust me there, but that is a strong sign of life for those of us who do this kind of work. So how do we get that strong sign of life? Besides all the stuff I told you about sample preparation, we use an instrument like this. This is called a secondary ion mass spectrometer. It's in a lab at Wisconsin where I worked before I came to JPL. You can see it takes up most of a very large room, and it has a 3-ton magnet there. So we're a long way from being able to fly a 3-ton magnet. But here are some of the things we do fly. So this is what we call our family picture. These are the instruments distributed about the rover. We'll start up here with META. META is contributed from Spain, and it is our weather station. It's like the REMS instrument on an MSL. We measure wind speed, temperature, humidity, pressure, other things. And then we move over here to SuperCam. It's a little hard to see, but this is the mast we call the remote sensing mast. So we have the body of the rover with its wheels. It then is a mast with some instruments at the top of the mast. One of them is SuperCam. Looks like a big eye on the top of the rover. That eye is a telescope that has a laser in the middle of it. So we fire the laser down at a rock several meters away. I'll just point here at SuperCam. We fire that laser like that, but it's a much higher energy laser than this one, and we create a plasma in the rock, and we do what's called laser-induced breakdown spectroscopy. And by doing that, we can measure the elemental chemistry of the rock that we've shot. Now, ChemCam on MSL, an instrument just like SuperCam, much like SuperCam on the Curiosity rover, could do that, but that's about where it stopped. SuperCam has those capabilities and builds on that with additional spectroscopic capabilities. One of them is called Raman spectroscopy that allows us to measure the molecular composition of the rock, including its mineral composition, potentially its organic composition. That's a partnership between France and the United States in the Los Alamos National Lab. Then we have MassCam Z. These are two identical zoom lenses. This is similar to the MassCam instrument on MSL. The MassCam instrument had a wide-angle camera and a zoom telephoto camera. Neither lens was a zoom lens. They were both fixed focal length lenses, sort of 35 to 100 millimeter ish. MassCam Z has two zoom lenses that encompass that full range. And so it gives us much more flexibility with our stereoscopic imaging for science. Then we move down here. Let's skip around here to MOXIE, we already talked about. That's the instrument that generates oxygen from carbon dioxide to test that technology. Then we have this instrument here called RIMFAX. This comes to us from Norway. It's a contributed instrument. It's really an antenna there that sits underneath the rover. And this is, for the first time on the surface of Mars, a ground-penetrating radar. So as we look around and see structures in our environment, see how the rocks in our environment are stacked together and penetrate from the surface with MassCam Z and our other cameras, RIMFAX will allow us to look into the subsurface and see how those structural relations continue into the subsurface. So that's a fantastic new capability. We have some calibration targets, but then let's blast back over here. This is the robotic arm. You can't tell that from this image, but it's in stowed position. And out on the end of the arm is the turret. And the turret has the drill, but it also has these two instruments, Pixel and Sherlock. Pixel is a microfocus X-ray fluorescence instrument. So it's similar in a sense in terms of its scientific niche to the APXS instrument on MSL that measured the elemental chemistry of rocks by placing the instrument down on the surface of a rock. Pixel, instead of measuring the bulk average chemistry of the rock, it shoots fires an X-ray beam, shines an X-ray beam, sort of is more appropriate, down on the surface of the rock, and the diameter of that beam is about the diameter of your hair, about 100 micrometers, and it scans that beam, it rasters that beam over an area about the size of a postage stamp, and instead of measuring just a bulk elemental composition, it makes maps of the elemental composition. So imagine a map of the silicon concentration in a rock. Imagine a map over that stromatolite that you saw, and I'll show you something like that in a moment. Sherlock is a laser-based instrument. It fires an ultraviolet laser, similar diameter, beam diameter to Pixel, about 100 microns, and it rasters that over a small area as well. And instead of measuring the elemental composition, now it's measuring the molecular composition through a combination of fluorescence and Raman spectroscopy. Okay, so we're measuring the molecular composition. We can detect, we can map the concentration of minerals that we know are important to life, like the carbonates I told you about earlier, but also of organic matter if there is any there. Okay. So just briefly, we land in a fresh new landing site, take a look around with MassCam Z, start to look at the textures and structures and colors in the environment, start to understand how the rocks there relate to each other. We peer into the subsurface with RIMFAX, with our ground-penetrating radar, take data that look like this. This is data from Svalbard, testing the RIMFAX instrument on a glacier that sits on top of rocks. So that gives you a sense of what the data might look like. All the time, we're measuring the weather with our META instrument. Here it is looking at a dust devil on Mars. And then we, as we look around with MassCam Z, we find rocks that look particularly interesting, and we shoot them with our laser, with SuperCam, and we look at them with the telescope in SuperCam, and we measure their chemistry from afar. So about as far as I am to the people over there, several meters away, several yards away, we can measure the chemistry of a rock remotely and decide, do we want to rove up to it and actually deploy our arm and do some more science? If we do decide that, we park up close to something and we deploy our arm, and out on the end of the turret, as I said, we have Pixel and Sherlock. Sherlock has a subsystem that we call Watson, funnily enough. Watson is a camera that's very similar, identical really, to the MALI instrument, the Mars Hand Lens Imager on the Curiosity rover. So Watson is our close-up scientific imager, like a macro lens that we take images from centimeters away from the target. And once we find something very interesting, we deploy a tool we call our braiding bit. So we switch our drill bits, we take the coring bit off, and we put on a bit that's designed to abrade, to flatten a circular area in the rock of about 45 centimeters. 4 centimeters in diameter. And then we have what we call a gas dust removal tool. So we have this just fantastic device that's full of very pure nitrogen. And after we've abraded our little circular spot that we'll later analyze, we need to get the dust that we've generated off of that area. And so we puff it with the gas dust removal tool, the GDIRT. So the GDRT, or the GDIRT, cleans it off for us. Then we switch to Pixel, and we make a map of the elemental composition. We switch back to Sherlock, make a map of the molecular composition, and if we like what we find, we deploy the drill, and we drill a hole. So on Mars 2020, we have a distinct investigation that's not associated with any one instrument on the rover, but it's meant to represent the interests of those scientists who would work on the samples if we're able to get them home one day, and that's called Return Sample Science, or RSS. We can also use SuperCam and Sherlock to make some measurements inside the borehole to get some sense of the chemistry of that sample that we've just chosen to put in the rover. So how do we do this part? How do we seek the signs of ancient life? I just want to show you an example here of how we do it on Earth using some of the Mars 2020 instruments. So this is a 3.4 billion-year-old stromatolite. This is from the same rock unit as the stromatolite that I've passed around to you, the Strelly Pool Formation, some of the oldest evidence for life on Earth. It's a fossil microbial mat, as we've talked about. You can see the textures, the morphologies, the shapes in the rock, these layers, these fine dark and light layers that are wrinkly. And if you study these things all the time, this looks very much to you like evidence of ancient life, a fossil microbial mat. If you don't, I don't know, it looks maybe like a mess, but get used to it. Get used to talking about stromatolites, because we're looking for them. In any case, Mars 2020 can recognize potential biosignatures, potential signs of ancient life, as lifelike patterns in the exploration environment. So that's pretty simple. We're looking for patterns in our exploration environment that are lifelike. Well, what does that mean? A little bit more technically. First of all, they could be concentrations of biologically important elements. What are those? Sometimes we call them chons or schnapps. CHONPS, carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. There are many others. Iron is important for life, but these are critical for life as we know it. We're looking for those elements. Minerals. What are the minerals? We've already talked about some carbonate minerals that are important for life, and sulfates and other types of minerals. Or molecules, organic matter. Okay, so concentrations of organic matter in a rock, particularly when they are spatially associated with biologically suggestive morphology. Okay, so it's especially exciting to us if we see those concentrations and they are aligned, they show variability or heterogeneity that is itself associated in space with a shape that looks like something that biology could have produced. So what does that look like? So we mapped this part of the stromatolite with the Pixel instrument, the laboratory version of Pixel, and we see the layered shapes now showing up not in a visible image, but in elemental maps. So green is showing silicon. That is where quartz has replaced the original carbonate. Carbonate is shown in blue. with calcium. So it's calcium magnesium carbonate, I told you. And the carbonate has variable iron concentration in it. So that's where you start to get the pink. And Abby Allwood, who's a JPL Stromatolite expert, and an expert in other things as well, but in especially Precambrian geology, she's the principal investigator of Pixel. And she published a study a number of years ago using a benchtop instrument to study this stromatolite and see this variable iron concentration as an additional piece of evidence that these stromatolites were biological. And it was that sparked the idea that now became Pixel. So next we mapped the same area with the Sherlock instrument. And Sherlock tells us about minerals and organic matter that's in the rock. And so you see quartz, where there's silicon, so that's good news. Quartz is silicon and oxygen. Quartz interspersed with dolomite, so that's the calcium magnesium carbonate I told you about. And then green, we're very excited about. Green is organic carbon, or a substance called kerogen. And this is complex macromolecular organic matter. It's not the same chemistry as the original organic matter that the microbes made. But the organics that the microbes made, subject to billions of years of geologic time, kind of smooshes together and combines into this complex substance called kerogen that itself can be preserved on billion-year timescales. So that is a kind of thing we'd be looking for on Mars, is kerogen concentrated into shapes like this. So this was very exciting, an early demonstration of the power of using these two JPL instruments together as part of the Mars 2020 payload, Pixel and Sherlock. Okay, just a few quick words on the sample and caching subsystem. So in what we call the flight system, that is all the parts of the spacecraft that are not the payload, all the science instruments we call the payload. The flight system is the big robot, the rover. The big new development in the flight system is the sampling and caching subsystem. So it's actually several robots in one. So we have the rover is a big robot. We have a robotic arm that has the turret with some scientific instruments, but also the drill, the coring drill. So that's a robot. And then we have the bit carousel. So the way this works is at the end of the robotic arm is the drill. When it comes time to drill, let's say we've just abraded a patch and we've deployed the gedirt and we've blown the gedirt off of the little area that we've abraded, and it's time now to sample. So we have our abrading bit on the end of the drill. We need to bring the robotic arm back to the bit carousel that you see there, that little circle on the front of it with a smaller purple circle in the middle. We dock the end of the robotic arm to that bit carousel, and we sit there for a moment. And there's some action happening now in the other robot, the adaptive caching assembly. Inside the adaptive caching assembly, you can see an inset here. There's another small helper arm. Okay, we call this the sample handling arm, the SHA. That little arm goes over and picks up a sample tube, a titanium sample tube, out of tube storage. You see here, we've got 42 there. It pulls out a sample tube, it brings it over, and it sticks it inside a drill bit that is sitting in the bit carousel. Okay, then the bit carousel rotates into position. We pull the abrading bit off of the end of the drill, and we swap it out for the coring bit that has a sample tube installed within it. Okay, now we're ready to drill, and we move the arm back over the target. We drill into the target, fill up that sample tube with rock or regolith. We have a special bit for collecting loose, unconsolidated material like soil, either a rock core or a regolith sample. We move back over to the bit carousel, and we put that filled sample, the drill bit with the filled sample tube now, rotate it back into the adaptive caching assembly. This little SHA, sample handling arm, grabs that sample tube and pulls it out and moves it through a number of stations. So we have a little camera inside there. We can take a picture of the very top of the sample. And then we move it to a sealing station. So we hermetically seal. We put a little sealing plug into the top of that sample and push it down tight so that we won't lose the volatile materials that are so precious inside that sample. We'll seal it up tight. We'll stick it back into tube storage, and it will sit there until it comes time for us to drop it on the surface of Mars. And just briefly, well, I'll quickly show you these sample tubes. But and so here's the coring bit. Here's what the sample tube looks like. These are not to scale, so the sample tube is obviously smaller than the drill bit. But that sits up in there. Here's a cutaway of a sample tube with a sample shown inside it with the seal, the gold seal. It's inside there. So sometimes we're collecting samples, but something that's very important for us to do in addition to collecting samples is to collect what we sometimes call blanks or witnesses. And this is important because we are working so hard on this mission to meet requirements that are really unprecedented with regard to our need to keep these samples clean. They're so precious that we have to keep them incredibly clean. That said, we can't keep them. It's impossible to do this sort of mission and keep them perfectly clean. So there will almost inevitably be some small trace amount of contamination. It's impossible to avoid, really. And we're going to keep that as low as possible, but we really want to understand, what is it? And so one of the things we do, we have some special tubes called witness tubes. And now we go over, grab that witness tube out, put it in a drill bit, put it in the drill, wave it around, maybe percuss it around in free space, treat it in every way exactly the same as we do a sample, with the exception of actually drilling into rock. Otherwise, it's exactly the same. And then we put it back, we seal it up, and we lock it away. Inside that tube is this fancy thing you see here, and we're getting to the end of our design of this, but it's pretty complex. But there's many different substances inside meant to monitor all different types of contamination that we think we might find, and some that we have no idea that we might find. And so we'll monitor that with these witnesses and seal them up, and we could bring those back along with the samples and analyze those. And anything we detect in these would be suspect if we detected it in our sample, right? So if we found some organic compound in here that suggested the presence of biology, if we found it in this and found it in our Mars sample, it'd be really hard for us to interpret that in a Mars sample as evidence for life. You get the picture. Okay. So that is coring and sampling. Before we go to landing sites, actually, just briefly want to tell you that the way we're doing this, so we drop individual sample tubes out on the surface one at a time. And so our basic model for exploration during our prime mission, which will be a couple Earth years, maybe up to 3 Earth years in our primary mission, we'll rove around. We want to explore 2 diverse regions of interest. Okay, so 2 areas that are about 1 kilometer on a side, imagine about that big. So if you're familiar with MSL, the whole area of Yellowknife Bay, all the work that we did there, that is similar to sort of a region of interest. But explore one part of our landing site. It's not possible to explore exhaustively our entire landing ellipse. So we divide that into 2 very diverse regions of interest. And we'll commit kind of about half of our mission, roughly, to each one. Maybe collect half of our samples in each one. But we'll rove out and explore region of interest 1, take a lot of measurements with our onboard instruments, collect samples, maybe about 10 samples. And then we'll keep those in storage, and we'll drive away to region of interest 2. Right on the border of region of interest 2, we'll start to drop our samples. We'll find a safe spot where those samples can sit for 10 years or so, if it takes that long. And we'll drop them one at a time in a collection that we call a depot. Okay, then we'll leave that spot, and we'll go and explore region of interest 2 and make a bunch more measurements of hopefully different, more interesting kinds of rocks. We'll collect maybe 10 more samples. We'll come back to that depot, and we'll drop our samples. And the reason we want to do that is as soon as we can offload those 10 samples or so, we've offloaded a huge amount of risk. We now have a collection of samples on the surface that the follow-on mission could come and return should something happen to our rover while exploring region of interest 2. Then we bring the samples from region of interest 2 back to the same place and drop those. Now we've offloaded more risk again, and we can start to go into, we hope, if we're lucky enough, extended missions where we can maybe take a bit more risk and go up that higher hill or over the horizon and do some more collecting there. Okay, so where are we thinking about going? We have, over the last several years, we've whittled down our list of landing sites from 30-ish or so down to 3, only 3. in a series of landing site workshops. These are open to the public. The next one is happening. It's generally scientists who come to these things. But we have 100, 200 even scientists who come from all over the world in some cases to help decide where we should send this precious asset of Mars 2020. Sometimes we vote at the end of these things, and it's sort of like the basketball tournament. We whittle it down to a top 8, and then down to a final 4, but in this case we were able to actually whittle it to 3 at the last landing site workshop. And interestingly, coincidentally, we selected 3 different landing sites that represent 3 very different ancient habitable environments. The first one is Jezero Crater. So Jezero and the second one, Northeast Syrtis, are close to each other on Mars, in the Isidis region of Mars. They're on the edge of one of the largest impact craters in the solar system. So a very large impact produced at a time when very large rocks were floating around the solar system. This was very early in planetary formation. That impact occurred, but then these environments formed out on the edge of that feature. And Jezero is in a smaller, slightly younger crater. And you see, it's a little bit maybe hard to see in this image, but here is the rim of the crater. There's a river that flows into the crater there, and out at the end of that river is a delta. A delta is a fantastic thing for planetary science because it's a feature that can be observed from orbit, which tells us there was a body of standing water into which another body of water flowed and dumped its sediment. Okay, that's how deltas form. So this river here that flowed into Jezero Crater dumped sediment there. And so bodies of standing water clearly are great places to go look for evidence of ancient life. In fact, almost everything we know about the history of life on Earth comes from shallow water environments, rocks deposited in shallow water environments. And so we know well how to search for evidence of ancient life here. There's a great mineral diversity here. We have clays, some igneous minerals, that might be particularly ancient, and then carbonate minerals here throughout the landing site, but these are particularly interesting to me. These are carbonate minerals up along the shore of what would have been an ancient lake. This is the type of environment where stromatolites form. So a very exciting place to go explore at Jezero. Northeast Syrtis now is a very different type of environment, more mysterious in a sense, older. It may be the oldest, certainly some of the oldest crust exposed at Mars, some of the oldest rocks we could possibly go explore on Mars. But these are not, we think, sedimentary rocks like these rocks here at Jezero. These are ancient igneous rocks. And the igneous rocks may have formed from volcanism, may have formed from impacts, so maybe earlier rocks that were melted by giant impacts occurring very early in the history of Mars. But then we have mineralogic evidence from orbit of the interaction of these igneous rocks with water a very, very long time ago. And so ancient water would have flowed through these rocks, through cracks in these rocks, dissolved bits of those rocks, and provided food for microorganisms that could have lived in those little fracture networks, potentially in hydrothermal systems that were generated by all the energy of those ancient impacts crashing into the rocks there. So that's Northeast Syrtis. And then Columbia Hills is in Gusev Crater. So this is where Spirit went. And the Spirit rover found these high silicon rocks. They're at the home plate area of the Columbia Hills. And in these high silicon rocks, were observed these digitate or finger-like morphologies. This is from a spirit image. And these finger-like morphologies formed in a high silicon rock suggests to some scientists that these rocks formed in a siliceous sinter environment, something like the environments you see in Yellowstone. So imagine a bubbling hot spring on the surface with water flowing out and bubbling through the rocks, hot water maybe dissolving things, reprecipitating things. So that sort of environment. There are some people who believe that these rocks preserve an environment like that, and some people take an alternative view. And so it's controversial, but we're We're now working through a lot of that controversy by studying these sites in greater detail than they've yet been studied. We have our science team working hard day after day. We just had a teleconference today about Northeast Syrtis, wrapping up months of hard work done by our science team on this site, all leading towards the next landing site workshop, which we expect will happen sometime this summer. And it's in the days, weeks, and months after that landing site that we hope that landing site selection workshop that we hope to whittle this down to a top site and a backup site. So the decision is not ours to make. We'll make a recommendation. The Mars 2020 mission will make a recommendation to the Mars Exploration Program, who will in turn make a recommendation to someone called the Associate Administrator of the Science Mission Directorate. Okay, this is sort of one level down from the NASA administrator. The different directorates at NASA. The Science Mission Directorate is largely in charge of missions like ours. It's the associate administrator of that group who is the true decider there, but we'll make a strong recommendation there of a top site and a backup. And we hope to have that site selected by late next summer or early in the fall. That would be 2 years prior to launch. So that gives us a big chunk of time to really focus on a single environment and go to analog environments that are like that on Earth and really study those in detail and really develop in great detail our exploration strategy that we will deploy when we finally do get to Mars. And so that is all I have for you today, except to show you this great sunset image. That's the sun setting at Mars, blue sun in a red sky. And then, of course, a URL. Stay tuned. Thanks for coming, and I'd love to take questions that you have. Thanks. Thanks a lot. Yeah, and please do come to the mic. So we've got someone there at the mic. Go ahead.
I haven't seen any solar panels. Can you talk about the energy source here and also about the communication capabilities?
Yeah. So you did notice there were no solar panels on the rover. So we have, just like the Curiosity rover for MSL, we have what's called the MMRTG, the Multi-Mission Radioisotope Thermal Generator. And so it's a nuclear power source. It generates heat, which is converted into electricity that runs our rover. So that's our power source. And then you asked about communication capabilities. We have also, like MSL, we have a direct-to-Earth antenna, so we can communicate. It's quite low bandwidth. We can communicate direct from the surface of Mars to Earth, and another antenna that allows us to communicate with our orbiters that are flying around Mars, orbiting around Mars, that then relay the data from the rover back to Earth through the Deep Space Network. And that's a much higher bandwidth way to communicate. So that's how we get our plans up to the rover and the data back down from the rover. Other questions? Yeah, if you could use the mic, thanks. That way the people on the video can hear.
Okay, you mentioned a safe place you're going to put the samples.
Yeah.
However, there are dust storms, 10 years worth of dust storms could cover that up. Is there going to be some kind of beacon to, like a GPS beacon or something to, tell you where they are?
Yeah, it's a good thought. It is something we're thinking about, definitely. There will be no beacon. There will be no active signaling done by the samples. They will have etched onto them unique identifiers that are machine readable. So we hope a robot could read those labels so we know which sample is which. But we won't have any kind of homing beacon or anything like that. But trust me, the site where those samples are dropped will be among the most exhaustively documented and the best known places in the known universe. So we will take many, many images, both from the ground, from that area, 360 panoramas and so forth. We don't have a GPS network around Mars yet, but we do have these orbiters, so we can take images and we can see the rovers from our orbiters. And so we'll take images like that if we still have those orbiters. And so we'll use that strategy and in order to get back, and maybe we'll still have wheel tracks leading up to it. But you're right, there is weather on Mars, there are dust storms, but we do understand those phenomena to some degree, not completely, but we'll choose our location very carefully with all of that in mind. Other questions? Yes, please.
With all these new sensors and new cameras, we're going to gather a lot of data. How have we evolved our data transmission techniques? Are we planning on sending a special antenna/satellite something to have a better communication and avoid the delay issues we had with, like, the delayed time between the rover itself and the mission control panel? So what are your thoughts on that?
That's a great question. I mean, that's one of our key concerns at this stage of development. We have this incredibly capable scientific payload capable of generating maps, so we can generate gobs of data. We can generate more data than MSL really was generating. We have more cameras that are, some of them are color now instead of black and white. So we have higher data requirements to get our science done. At the same time, the orbiters around Mars are aging, and NASA does not have a plan yet, official, to send another orbiter to back up those. But we do have multiple orbiters around Mars currently. We have MRO, we have Mars Odyssey. I won't list them so I don't forget any. But anyway, we have MAVEN, newly in orbit. But we're in conversation with all of those teams and with the Mars Exploration Program to figure out the best way to get the bandwidth we need to get the data down. There's no way, unfortunately, really, that we know of yet to minimize that time of communication. That gets down to the speed of light, but it's getting the data rate, getting the bandwidth that we can across the DSN is one of our key concerns. And so it may indeed partly be international partnership. The Europeans have orbiters in place, and we'll partner with them as well as using NASA assets. So we hope to do all of that. Thanks. Other questions? Yep. Oh, let's take yours and then make sure I don't forget. Let's get one from online. We have some people online, but you go ahead.
Hi, could you talk a little bit about the process where you talked about the different instruments that tested an area before you decided to dig? What's the time lapse between the scientists being able to evaluate each of those stages and when it actually, you know, there's many decisions there?
Yeah, another fantastic question. So that, you know, these are really hitting on the key issues that we spend so much time talking about. She's asking about the time between when the scientists get the data or we run the experiments on Mars, the time between that point and when we collect the samples. Obviously, it takes time to get the data down, as we were last talking about, to get the data from Mars to Earth. Sometimes it's not just the latency between Mars and Earth. It actually takes days, or in some cases weeks, to get all the data down, because we have critical engineering data that we need day after day to assess the safety of the rover. So that's very high priority. And then in some cases for these large science experiments, we slowly get the data and assemble these maps, those elemental maps and molecular maps I showed you. May take a while, may take days to get down. And then the data are down, they're in a raw form, and the scientists have to process them and crunch them and then you know, put together those beautiful maps that you see. And then, only then, can they start to make sense of it. And that doesn't happen instantly, and that can certainly take days or weeks. And so partly for that reason, partly for some other reason, we're employing a strategy we call the walkabout. Okay? And this is as distinct from maybe a linear strategy. So imagine we're roving along, and let's take the example of MSL roving from its landing site close to Yellowknife Bay to Mount Sharp. You can imagine the linear approach there, roving from this place to that place along the way, taking scientific data, collecting samples, processing them in the rover, moving on to the next place. Now imagine, you know, 6 months after you were back at some interesting place and you find something new in the data and you say, oh, wow, that's incredible. We need to go back. That's a very hard decision to make, right? To turn around that rover and drive all the way back to that place and look at that place again. And so we are organizing ourselves based on some things that MSL has developed at a place called Pahrump, where the Pahrump Hills, this was a place right at the base of Mount Sharp near the end of MSL's primary mission for their first extended mission, where they drove in loops. Okay, so we organize our exploration of this environment into 3 loops. It could be 2 loops, it could be 4 loops, but let's say 3. And imagine the first loop, so you get to your campaign location. We call this thing a campaign, a walkabout campaign. We get to the edge of that campaign area. Maybe we find a local topographic high from which we can get a nice expansive view of our whole campaign area. We take those images, then we rove into the campaign area, and we decide where in that area we want to stop based on that first imaging stop, some interesting spots. We stop at each of those and we deploy our remote instruments, MassCam II and SuperCam, to take some remote science data, but we have the discipline to move on to the next stop. We don't dally, okay, at these stops. We get that first loop done and get back to close to the starting point, just roving from stop to stop to stop, collecting a bunch of data along the way. Now, once we're back, we have a lot more data about that campaign location, and we understand it better. Certainly not completely, but we understand it better than we did when we arrived. Based on that information, we decide which of those stops, or maybe some different stops, to take to deploy our more complex instruments out at the end of the arm. So we do what we call a proximity science loop. The first one was a remote science loop. The next one is a proximity science loop. We drive around roughly the same route, stopping at certain places, probably fewer places, because the proximity experiments take more time and energy and complexity than the remote science experiments generally do. We deploy our robotic arm, a braid, Gedert, Pixel, Sherlock, and so forth. But again, we maintain the discipline not to dally and to move on to the next spot and get ourselves back roughly to our starting place. And it's in all that time that we hope the data are pouring in and the interpretations are happening. The scientists are working as efficiently as possible to make some sense of all the data as they're coming down. And then we can decide which of those places is most interesting and should we go sample. And at that point, we can go back and take a sample, process the data, continue to process the data from these later stops and decide which of those we want to sample and so forth. So that third loop might be a sampling loop. So that's basically our walkabout strategy that we're going to use. Hopefully that answers the question. Oh yeah, online. Okay, a couple online questions. Shannon asks, were there changes mechanically and or to software on 2020 based on what we learned from Curiosity and other previous missions? Absolutely. So there were changes. As I said earlier, we take a heritage approach. So as much as possible, we do what we call build to print. So we take advantage of those great designs from MSL and build the rover as similarly as possible. But we do change some things. I mentioned the wheels. And of course, software. In some cases, it's easier to change software than hardware. And we are doing a lot of new things with software. So a big focus on autonomy. This is sort of obviously a wave of the future in our homes and on Mars. I have a robotic vacuum I just bought that autonomously vacuums my house. So we use very similar technology, I'm sure, to what that vacuum uses to drive the rover around and avoid obstacles on its own. But also, amazingly, to many people, to me included, autonomously to select targets with very high accuracy. So we can program some parameters into the robot and say, we are really interested in these rocks we've been seeing that have a brightness and albedo between X and Y. So we like rocks that have about this color or this brightness that tend to be flat along our route. So if you see rocks like that, take pictures, robot, along the drive. As you see rocks like that, shoot them with SuperCam. Okay, MSL has started doing this. It's a piece of software called Aegis, and it has something like over 90% accuracy with its targets. So when you show up at the end of the drive and you look back at the pictures that it took and the things that it shot, over 90% of the time, I think it's well over 90% of the time, it shoots just the kind of stuff that we were looking for. So this is fantastic in many ways. It's just fun and interesting that the robot is shooting targets that it chooses itself in a sense, but also it allows us to offload some of the more systematic measurements that we want to make. As we're roving across some new terrain, one of the things we want to do is just take some basic measurements every so often and understand basically how the chemistry or morphology of those rocks are changing as we rove across the territory. When we show up at a parking spot, if we don't have something like Aegis, we would have to spend our scientific planning time to say, okay, first we have to take those systematic measurements before we can shoot that interesting shiny thing over there. You know, but with Aegis, you've already got those in the bag, and you can focus on the shiny thing. So we make some really interesting discoveries that way. Yeah.
Two things. One, how exactly do you ensure that the rover and all the component parts and instruments with all the little pieces of them, the sky crane, all the things that would be in contact with it, that they are not contaminated by Earth microbes that could potentially complicate your results? And the second thing is, you mentioned about software updates. So, you know, on Earth, I know, like, for example, Tesla, the car manufacturer, can beam software updates to cars that, without the owner of the car having to bring it in somewhere to get it updated. Can you do that from 35 million miles away?
Yes. But we're very, very careful when we do that, and we try to minimize the times that we do those software updates, but it is possible. So that's the second question. We can do that. And I'll just read the next online question before I answer your first one, because they're sort of similar. The online question doesn't say from whom, but has there been more discussion of exploring Mars's recurring slope lineae, dark streaks without risk of contamination? So this gets to your point, I think, which was how do we ensure that all those pieces and parts aren't contaminated by Earth microbes? I see some folks in the audience here from our planetary protection group. Yeah, raise your hands if you're from planetary protection. Hey! That's right. They deserve applause. These are protectors of the planet Mars, also protectors of the planet Earth. So planetary protection works in two directions, at least two directions. Sometimes it feels like it's coming from every direction. But we do what we call we protect against what we call forward contamination. That is, we work to minimize the extent to which we deliver Earth microbes to Mars. It is impossible, as far as we know, to build a robot like anywhere close to this complex and have it be completely 100% sterile or free from Earth microbes. By completely sterilizing like that, you destroy a lot of the modern technologies that we employ on this rover, the computers, the power source, the MMRTG. They can be cleaned very, very well, and they are cleaned very, very well, but they can't be completely 100% sterilized. And so we monitor that. These folks who raise their hands are the ones who monitor that day after day. They monitor spacecraft surfaces, all the labs where the clean rooms where the rover's being assembled. They're collecting little witness plates. I showed you the witness tubes. They have their own version, little coupons, witness plates that sit out in the clean room and just have things fall on them, bacteria and so forth. And so they do these swabs and analyze the microbes that are on the rover. We call that the bioburden. We try to knock down that bioburden as low as we possibly can. We have some very stringent requirements from NASA on how low that must be. Okay, MSL met those requirements very well with margin, and so we're using the same techniques that MSL used to keep that bioburden low and minimize forward contamination. Now that's one side of planetary protection, and it's particularly relevant to this question about recurring slope lineae. So these are these dark streaks that form sometimes on the edges, the walls of craters, where you see they appear as dark and then they go away, they fade away. Potentially it's evidence for seeping water, maybe very salty water on Mars. These would be prime targets if you were going to investigate potential extant life on Mars, because it's a place where liquid water might currently exist at the surface. We can't get anywhere near those things because we're not a mission that's designed to do that. We're a mission that's designed to go look for evidence of ancient life, and we get as clean as we need to do that. You'd have to be even cleaner to go look at those recurring slope lineae. So we have no plans to do that. Maybe a future mission, hopefully a future mission will go do that. That's not our job. But we are, because we are the outbound leg of a possible Mars sample return mission, we are now concerned with backward contamination. That is, potentially, if we take a rock sample that contains viable Martian microbe that is harmful to Earth life, we could bring that back, and if that were allowed to be opened and have access to the Earth environment and escape from some containment facility, it could be bad. Now, we take that possibility extremely seriously, and we work very hard to do everything we can to not have that happen, including we have a requirement that in every sample we collect, it be completely free from Earth organisms. Okay, so we are so clean that we need to show before we can launch that every sample we take will be completely sterile. Not the whole rover itself, but the sample itself will be sterile so that, number one, we give the scientists the best chance to find any evidence of life that's in those samples. And number two, we don't get confused between Earth life and potential Mars life. Now, I think it would be very difficult for us to be confused for reasons I won't go into because we're over time already. But it's also something that is unlikely. So pieces of Mars do exist on Earth. In a sense, we do have samples from Mars, and these are the meteorites. So Earth and Mars have been exchanging material for eons, okay? So it's not as if these samples we bring back are the first pieces of Mars ever to come to Earth. Now, that said, if they come back, they will be delivered very carefully to some facility, some receiving facility that may have a higher level of biosecurity than any that currently exists. This is sort of a CDC type, think CDC, biosafety level 5 or whatever you call it. Very, very secure, and they will not be released probably until they're sterilized or somehow we are totally confident that they're free from anything dangerous. Another question. Okay, it looks like this will be the last question.
Can you tell us a bit more about how the machine that converts carbon dioxide to oxygen works, and if you have any plans for it?
Well, I can't tell you too much about it, not because it's a big secret, but because it's a kind of physics and chemistry that's not really my key area, but we call the technique solid oxide electrolysis, okay? And so we take CO2 in, and then we react that in what we call the SOXY stack, the solid oxide electrolysis stack, and we basically pull the oxygen off of that CO2 molecule and generate CO and O, and the O combines to O2 as oxygen. Is that what you're looking for, or something even more technical? I can definitely point you to more details that you can read. But plans for it, it's to use it and test it out and put it through its paces. We're particularly interested to understand how does it work in the dust environment of Mars. So there's a little filter out on the inlet where the CO2 comes in. Over the course of our mission, that will collect dust. So what is the pace at which MOXIE becomes less and less effective as dust builds up? That's one example of a question that would clearly be very important to understand if you're going to send one of these things that's 100 times larger and more expensive to the surface of Mars. So we really want to push it over the course of our mission potentially to failure and understand how and why and when does it break after getting a lot of great data out of it, hopefully. Okay, so that's all. I'm still around. I'm happy to have you grab me. Don't grab me, but find me, and I can answer questions if you've got any burning ones. But thanks again so much for coming and for putting this together.